Hi class, this is Mr. Morris. This is Unit 3.11, Spectroscopy and Electromagnetic Spectrum in AP Chemistry. These notes should go fairly quickly. We've got electromagnetic radiation. We're going to review what that is. First of all, it is a form of energy that exhibits wave-like behavior as it travels through space. Different types of electromagnetic radiation are ultraviolet light, the most common one, visible light, infrared radiation, microwaves, television and radio signals, X-rays, also gamma radiation, and there are other forms of radiation, but these are the ones that we talk about the most often. If you look at the electromagnetic spectrum that we have here, going from left to right on this spectrum, you can see that the wavelength is increasing. It's getting bigger. If you look at the frequency scale, which is on the bottom, it's getting smaller going from left to right, and you can notice that from looking at the numbers going from 10 to the 20th to 10 to the 8th. It's getting smaller. And then we don't really have numbers here, but we know the highest energy is on the left and the lowest energy is on the right. So what can we conclude from this diagram? Well, if we have high energy, if we have long wavelength, then we're going to have low frequency. And if we have low frequency, we will also have low energy. Okay. On the other hand, if we have a short wavelength, we're going to have high frequency and high energy. It's important to recognize the relationship between wavelength, frequency, and energy. So if we have long wavelength, we have low frequency. Those are inversely related. Okay, energy is inversely related with wavelength, and frequency and energy are directly related. So make sure that you recognize that. Spectroscopy, this is the part that's kind of new. Spectroscopy is the study of interaction between matter and electromagnetic radiation. So by using spectroscopy, we can learn how atoms or molecules move and how the energy stored in them, in an atom or a molecule, how it's stored, how the energy is stored. We're going to talk about several different types of energy or ways that a molecule or atom can store energy. But keep in mind, the way that we're going to do spectroscopy is you shine some form of radiation, shining a light or exposing it to X-ray radiation or gamma radiation or something. You're exposing a sample to radiation, and then you've got a detector or a reader that reads out how that impacts the radiation as it passes through the sample. So molecules can store energy in 4 different ways. Translation, that means the whole molecule is moving in X, Y, or Z coordinates. So if we have a molecule, it would just move. It moves to the left, to the right, up, down, forward, backwards, or at some angle, but the molecule itself is moving. Okay? Rotation, that means the whole molecule is rotating. So it may not be moving around, but it's spinning on an axis. Okay, so it's rotating on some axis. Vibration means that the bonds are stretching or contracting. So the bonds between the atoms, so say we've got 2 atoms that they separate from each other a little bit and then get closer together. So they're expanding and contracting that bond. They're getting closer together, farther apart. Okay, that's called vibration. Then electronic energy storage, that is when electrons will jump to a higher energy level or fall to a lower energy level. So it's a transition between the ground state and an excited state. The energy absorbed in electronic transitions is usually the UV visible range. So that is electronic transitions. Okay, that's usually either ultraviolet or visible range. We often abbreviate that UV vis. Okay, the energy absorbed for vibrations, so if we're analyzing vibrations in molecules, that's usually in the infrared range. So the type of radiation we would use is infrared radiation. The energy absorbed for rotations is the microwave range, which is lower energy still. And then the energy absorbed for translations is really, really, really small. So that's not really an analytical technique we use much. We just know that atoms and molecules, they move around fairly easily. It doesn't take a lot of energy to do that. Okay, this is because electronic transitions require the most energy. Okay. And then it goes from there. Then vibrations, then rotations, and finally translation requires the least. So if you recall when we talked about electron configurations, if you put energy into an atom or molecule, the electron would jump up to a higher energy level. Maybe it's in the 3rd energy level, it jumps up to the 4th, or maybe it's in the 3s and it goes up to the 4p or something like that. Okay, this figure just shows an energy diagram showing the relative energies of rotational, vibrational, and electronic transitions and how they overlap. So energy is increasing here. Rotational energy levels are in this area. Okay, electronic transitions require a little more energy than that. Okay, vibrational energy levels somewhere in here, and then when we talk about translational, it's not even on here because it's such a low energy. So translation requires the lowest energy. That means it would require the lowest frequency of radiation, and that is the longest wavelength of radiation. Rotation is next, then vibration, then in electronic transitions, that's the highest energy, which is the highest frequency, and it has to be the shortest wavelength to make those things happen, to make electronic transitions occur. Here's another graphic that gives a little bit more detail on it. Okay, we've got different types of radiation that are used in an analytical technique in this column. Then we have the relative energy. The lowest is down here, microwave radiation. The highest is X-ray radiation. And yes, you could go as high as gamma, but we don't really do that with chemical analysis. What does it do to the atom or molecule? And we're going to go through that. What it tells us about the atom or molecule, and then the name of the type of spectroscopy that is used there. Okay, let's start with X-ray, if we're using X-rays. This is so powerful it can remove the core electrons. Remember, the core electrons are the hardest to take away because they're the closest to the nucleus and there's a lot of other electrons in the way. So you have to remove the outer electrons and get all the way down to the core electrons and remove them from the highest, from the lowest principal energy level, which requires the largest amount of ionization energy. Okay. So we can use an X-ray to do that, to take core electrons off of an atom or molecule. This measures how tightly electrons are held by the nucleus. Okay. Photoelectron spectroscopy is the type of spectroscopy we use for that, and we talked about that in the electron configuration topic. Ultraviolet radiation can also remove valence electrons at the higher end, at the higher energy end of the ultraviolet range. It can measure how tightly electrons are held by the nucleus, if that's what we're doing, if we're using ultraviolet for photoelectron spectroscopy. Okay. But on the lower energy end of ultraviolet, it can be used to excite valence electrons, and that determines the identity and concentration of a molecule. If we're just exciting the electrons to a higher energy level, that's UV-vis spectroscopy, ultraviolet and visible range. We call that UV-vis spectroscopy. It's used to tell us what the molecule is. Okay, and we can do that with either low energy ultraviolet light or with visible light to excite the valence electrons and determine the identity of the and concentration of the molecule. We have some spectrometers that we typically do a lab with that are UV-vis spectrometers. We will probably try to do a demo with them at some point. Infrared. is a little lower in energy. This just changes the vibrations in bonds, and it helps you to identify the types of bonds and functional groups in a molecule. The vibration, remember, that's a change in the distance between the atoms. So the bond length is expanding, contracting, expanding, contracting. So if we are doing that by exposing it to infrared radiation, it makes sense that we would be able to tell just how long and how strong the bond is by how much vibration that occurs when we subject it to infrared radiation. This is called infrared spectroscopy or IR spectroscopy, and sometimes we call it vibrational spectroscopy. And then finally, microwave radiation can be used to change the rotations of atoms or bonds, so changing the direction that they're rotating on an axis. This identifies the locations of hydrogen atoms in a molecule. We call it microwave spectroscopy or rotational spectroscopy. Let's look at an example right here. We've got a diagram above that represents the absorption spectrum for a pure molecular substance. And we want to know which of the following correctly indicates the type of transitions observed for the substance in each of the regions on the absorption spectrum. At the high end, ultraviolet and visible, so in this high end, ultraviolet and visible, we can tell the identity of the molecule because we're exciting valence electrons. Okay, that's UV vis, right? So we're exciting the valence electrons. We've got an electronic transition there at the higher end of our energy, the higher energy radiation. Then we have infrared in region Y. In infrared, we said that we could only change vibrations in the bonds. Okay, so electron transitions, vibrations in the bonds, and then microwave radiation is just rotations. Okay, so which one correctly ranks these? Region X, Y, and Z. X is going to be the highest energy. That's electron transition, so it's got to be either B or C, or I'm sorry, B or D. Okay. Molecular rotation would be microwave radiation. So that would be in region Z. And molecular vibration, that's infrared. So the correct answer here